Professor Sudhan Majhi for his talk.
Good morning, everyone. Am I audible? Yes. Okay.
Yes, sir.
Okay. So, as thank you very much, first of all, Professor Singh, for giving this opportunity and for
Last one. Go to last one.
this one. Share this one.
Go to third. Then click here. Okay. This one. Pencil this one. Pencil here.
So yeah, thank you. So let us first spend some time that why we are jumping to AIML and for 6G communication. So there are except some advancement in terms of results and application, there are some fundamental limit as well for the conventional statistical based method when we apply for prediction estimation. So let's see this equation that y equal to hx plus w, y is the received signal, h is the channel modeling, x is the transmitted signal, and w is AWCN. So now you see, if we need to calculate the BER or any performance metric, what do we need to do? There are some assumptions. For example, W is the additive by Gaussian noise, and H is either Rayleigh fading or Russian fading or Nakagami fading. But think about this is some kind of model we made. If we do not make this WAW is a AWGN, then deriving BER or any performance metric would be very difficult. We would not get a closed form. So then the question is that, okay, but still whatever assumption we are making, still we are able to apply in practical scenario. Yes, the answer is correct, but when we get some BER, but when we try to apply in practical, there is a 5 dB, 6 dB, 7 dB loss. Okay, so that loss always will be there. Why? Because whatever the exact channel model in practically, that may not we are getting when we are deriving the theoretically. Okay, so that gap always create problem. You know that when we do some kind of analysis in theory, we are having still doubt. Is it okay to apply practically? So then there need to some transform to verify whether this theoretical model will be accepted or not. And that is the reason you can see that we are having so many papers, so many methods, so many models, algorithms in literature. But are we applying all them for practical application? No, right? Because we do not know that which of the algorithm will be practically feasible or not. That is a fundamental limit for deriving statistically and applying practically. But if we convert them to machine learning, so you know, machine learning, whatever signal W noise will be receiving from the practical, okay? So the model will be trained by the same channel. So there is no assumption. We are not, yes. If you are creating a synthesis data and if you are training the model, that is a different story. But if you are receiving the signal and whatever W, it may not be AWGN. It could be other kind of things, but it doesn't matter to AIML model that will train the practical channel and then give you the test results. Okay, So you can see that, and that is the reason when we develop any algorithm AIML model, and when we do the practically, the loss is very, very minimal, very, very minimal. And that is named the reason that AIML model becoming very powerful technique. This is fundamental. The other things are there. I'll slowly disclose them. So as I said that you can see that performance loss very less. Okay, and many complex problem can be solved. Whether we understand or derive, that is different story. But if you are having model, if you are having data set, you train the model, at least you will be getting the results. But to make these results very perfect, 100% accuracy, then you need to play a lot of things. Okay, and then it's a kind of automation, flexible, and many complex problem can be solved. Okay, so other than this, for 6G, if you think, these are the main things we are looking for. Spectrum efficiency. This is not 6G, even 3G to 4G, 4G to 5G, 5G to 6G. Everyone looking for spectrum efficiency, right? Otherwise, it's very difficult to increase the data rate. And then energy efficiency, another pillar, so that we can move to the green communication. And another is that computational efficiency, so that latency can be improved. So you can see that now the question is that how AIML doing all these things. So we have a frame structure. Any communication frame, 5G or 6G, there is some payload data, many things are there. And it is well proved that we can omit some of the payloads or preamble for channel estimation or any kind of estimation. We can remove some. Now, if we remove some of the redundant bit, and still we could be able to detect the signal or estimate the channel, don't you think that this is a better way, so that we can save some of the bits? That nothing but improve the spectrum efficiency. Energy efficiency, since we are removing some payloads or some preamble, this means that we no need to transmit some of the bits. That means we can save some of the power amplitude, right? And then again, since your frame get reduced, so that if you perform any algorithm, obviously the frame structure vector it get reduced. Obviously, the computational time also will be reduced. Okay, so that it become a very faster. So this way you can think that by developing AIML, not only it's removing the fundamental limit, not only also giving adaptation, intelligent. Okay, so it's also helping. So other three pillars, which is always exist for 2G, 3G, 4G, 5G. Okay, so that is the main motivation of bringing this AIML for 5G and beyond and 6. Okay, so now let us move to this. This is a diagram I have taken from, but I modified a little bit that diagram. So some of the things we have not mentioned, but source is nothing but a source coding. We can show that source is coming, and these are the head block. So those block we are targeting for developing AIML. Okay, and I'll tell what is the reason behind it. I'll spend most of the time here. Then some of the application we'll discuss. Okay, so if we understand the logic why we need first a block, and then later implementing them either by supervised learning or reinforcement learning, those are not very big deal. Okay, but why we need to bring those AIML models here. For example, this is a joint source and channel coding. Joint source and channel coding. So you can see the source coding. What is the objective? Compress the data. Compress the data so that we can efficiently storage the storage efficiency. Many things we can do. But then after one or two blocks, we do the channel coding. What is the objective of channel coding? That increase the dimension, increase the bits, so that the error will be reduced. So you can see that. But those we are in the current scenario, we are doing them independently. So we are, when compressing, we do not take care about this modulation, the channel coding, and when we are doing the channel coding, we do not take care of this. But between these two, when we are doing the source coding, and if we could look at the channel coding, and when we are doing the channel coding, if we look at the source coding, then some of the bits we may save. Okay, some of this redundancy or some of the departments we can look. Okay, and that is the reason if you go to the release 20 3GPP standard, so they have some kind of study material. Okay, so that can we apply AIML model for source joint source and channel coding. Okay, so this is a study material. I think it will be another 6 months or 6 months we'll be studying. We'll be doing a lot of debugging, that whether it is helping to 6G or not, and then based on the conclusions of different or output from the academia and industry, we'll freeze it whether we are going to apply AIML model for the source. So now object is clear. Now AIML scrambling. Okay, so this scrambling. So you know what is the objective of scrambling, right? So scrambling and interdeliver is a kind of giving the diversity of the threading. So if you are having some threading, severe threading, and some of the data may get corrupted, okay, so that we do the scrambling and interdeliver so that they distributed this threading across the bits so that bit error rate can be improved. Okay, that is not only one object. The second object is the scrambler to hiding the data. So it is also play a kind of security mechanism. Okay, okay. And now, if you are using a deterministic scrambling, means you fix the scrambling for specific. Now, if this scrambling is known by the receiver or the eavesdropper, they can one step ahead to decrypt your data. So scrambling sometimes we use for the encryption as well. Okay, but this scrambling is fixed. So anytime if any eavesdropper come to know this scrambling, then your data is one step down to be decrypted, right? So that is the result. Now the question is coming that, and also this scrambling also depends on the channel CSI. So that some CSI that scrambling may be good and some scrambling. So what I'm trying to say that the scrambling also dependent with the CSI. In the conventional system, now we are having a fixed scrambling. But if we are having some kind of CSI-based scrambling, then we need to adapt this scrambling. Okay, so that you can improve your security, because scrambling, even if the know your scrambling for this moment, but the next moment we do not know what kind of scrambling will be coming. So that will decide. AIML blocks will be decided. Some kind of work, industrial work is going on. That how to scramble, develop the scrambling by AIML, and based on the input of CSI. Okay, and then whatever scrambling you are doing, obviously you have to do the scrambling. So if you see this and this is a kind of encoding mechanism, and this is a decoding mechanism. So we call such kind of model is a two-sided model. So when we train by using two-sided model, we keep an input and output that create the loss function. Then we develop this model. But when we place this model, testing model, so one part of the training we put at the transmitter, one part of the we put it at the receiver. And this two-sided model is a very, very common practice in 3GPP 5G for, let's say, channel compression feedback. Okay, many places we use this two-sided model. But there are some other research direction that when you are having two-sided model, so that how to that if you are training two-sided model by yourself, and then if the network belongs to the other service provider or UAE belongs to the other manufacturer, how to protect your model, how to create the IP. A lot of things are going on, a lot of research direction. The two-sided model is a very, very powerful model, but need to protect your IP. Okay, so that lot of work is going on, and then also when you place this model, so you have to find that this model may be suitable for your network, for your device, but this may not be compatible to the other network. Let's say you Samsung develop such kind of code for their specific base station, and this may not be suitable for this Nokia base station. But again, if you share, then you can place, but then will you be able to protect your IP? So many work is going on in terms of 3GPP standard and 5G. Okay, same, and this is a the new kind of topic. It's introducing. There will be two things. So either we are now also studying this one and this one. What is AI/ML modulation? I'll be describing how we have developed. But before going to that algorithm part, AI/ML modulation means that the channel could be severe, channel could be very good. So in the case of when channel is good, we try to achieve as much as better data rate, right? But when channel is severe, we try to reduce the data rate because we cannot able to cope up the BER. Because there is some target quality of service that okay, 10⁻⁵ at 10 dB, I need to maintain this BER. Okay, but then due to this CSI change, what we do? We change even Wi-Fi, even 5G. But when it changes modulation, so there is the NCS thing. So NCS lookup table we keep at the transmitter, and also we keep at the UE side. And then every time when we change the modulation scheme, we send some index. Okay, this may be 4 bits or 5 bits. So now currently we are changing within 4 to 8 modulation scheme. But let's say 6G, we will be jumping from BPSK to 1024 or 2048. Now, how many bits we need to transmit? How many bits we need to transmit to inform that what kind of, maybe 6 or 7, and 6 or 7 bits required to change the index of the table. We will not send in the table. NCS table will be stored at the base station. It will be stored in the UE. Now, one storage is required. This is called the lookup table. But then, which lookup table or which row has to be used? That information we say by index. Okay, this index could be 6 bits or 7 bits, whatever. Now, the 6 to 7 bits we cannot send directly because we have to do some channel coding, because otherwise whatever bits we are transmitting, if there is a loss, then we cannot able to retrieve. So then think about that 6 bits, and this how every 1 millisecond time, 1 millisecond or some periodic, let's say 10 millisecond time, we need to send this information. Don't you think this is a kind of redundant bit? This is a kind of wasting our spectrum efficiency. Now, what we can do that based on the CSI, we'll develop the AI/ML model, which will predict that okay, what would be the better modulation scheme, so that we can satisfy our quality of service, and also along with we can able to transmit the data successfully. So that is the one method we are talking about, the AI/ML modulation. And similar kind of modulation also, some AI block will be at the receiver, which will predict what kind of demodulation is.
Every packet follow a different demodulation scheme, or if there are like a set of packets, so like every 4 or 5 packets there's demodulation scheme.
Yeah, not every packet, and not always need to be changed based on the CSI. Let's say channel is does not change similar to the good channel. There is some, for example, raining time. So raining during this monsoon time, and some it's a 2 or 3 hours. Okay, that time the channel will be one type of CSI. Right? So I don't need to change the data rate often. Okay, so based on the channel condition, right? Okay, if it's very drastic. So let's say you are using very high speed mobility and you are sending some kind of plastics. So there you may need to say, but again, this changes not every time. It could be 1 second, 1 minute, 1 hour, but that has to be automated. The question is that we will not do by manually. It will be done by automated, and will not utilize any redundant bit for that. Did you get it? So now, then all the receiver also will be having some kind of modulation, and then a demodulation classification, that what kind of modulation, but without having any pilot or preamble. So from the signal itself, we could be able to classify that what modulation scheme it is, and then we'll use this remodulation. And a lot of work we have done in this direction. Many people have done this direction, and we able to reach 96%, 99% accuracy. Okay, this is the AI/ML based modulation. Then this is another recent study came that what kind of modulation we talk, that from the set of modulation scheme, GPSK, 16 QAM or whatever you select. Okay, but all these modulation scheme are kind of linear. Okay, but that linear modulation scheme sometimes is not optimal. So can we develop a nonlinear modulation, like there is a there are many structure kind of nonlinear modulation. So they prove that they are optimal, but designing such kind of modulation scheme is not so easy. Okay, so the question is that can we develop a AI/ML model which will produce a nonlinear and optimum modulation scheme at the transmitter, and similar set of modulation scheme we place at the receiver, so that we can generate a nonlinear based modulation scheme. Okay, so that we can see, and also you can see that if it is a OFDM, we get a lot of PATR problem, peak average power ratio problem. So, and peak average power ratio problem is a it's a very important topic. When we use for 5G or 4G, so the downlink communication is the OFDM, but uplink communication is not OFDM. It is a SCFDMA, or is called spreaded OFDM. What does it mean? That means that for downlink communication, we are having very sophisticated base station where we can place a sophisticated power amplifier. Okay, so that it's not very difficult. Okay, but if we want to implement such sophisticated power amplifier for the uplink, we cannot. The cost of UAE will be very high, and also it's very difficult to also implement this amplifier at the for the downlink communication. So you can see that although both devices same, but the uplink and downlink, the technology we are changing. Why? Because of this PATR problem. SCFDMA is a one method. We introduce one IFFT and FFT extra block, which reduce this PATR. Okay, so now the question is that can we use OFDM for uplink and downlink both? And what about the power problem, PATR problem for the uplink? That can be reduced by AI. Okay, and some sort of work already started, but what problem currently we are facing, we could be able to reduce this PATR for uplink, but the quality of service we are not able to maintain. Okay, so what is the PATR? PATR is the things that when we use OFDM, that there are several randomness will be coming, and some of the randomness, when we convert to the time domain signal, it will go very high peak and then it will low. So that peak average power ratio, that is the highest point, and average, if we divide, and if it is a greater than means what value. So for conventional system, it is a greater than 12 dB or 15 dB, 16 dB. If it is 16 dB, we cannot handle anymore. Okay, so the things we need to keep below the 10 dB or 8 dB, so that the longevity of this power amplifier will be high, and also nonlinearity of the power will be. Okay, so such way, so we can do this PATR. So what actually we do? There is a AI/ML model which can create a randomness to the input bit, so that PATR will be less. Okay, and based on that, this randomness will be created at the transmitter, and whatever randomness will be coming to the receiver, that will be reverted back to the original bits. Okay, that is the things, but a lot of work is going on this direction. So now this is a transmitter part. Now similar kind of things also will be receiver, but another new things we are bringing here, that AI/ML based HARP. So you can see that this HARP usually when we implement, so after all this process, it's come to here, then channel decoding here, then we use some kind of cyclic redundancy check. Based on that, we check whether the packet is success or not. Okay. Now you think that if the packet is success, fine. If the packet is not success, then this LTPC decoding is the iterative method, create latency, and all this block will be creating a lot of latencies. Okay. Now we spent some time, and after that we came to know that packet is going to success or not. So you can see that low latency, or 6G, we are looking ultra low latency communication. But if there is a error, then latency already will be introduced. Now we'll activate the HARQ. So this is, if you see the conventional system. But what we are trying to do is that if the packet is success, fine. If packet is not success, we'll take the signal from the receiver itself, and then we'll develop AI/ML model, and we'll tell there by training the model that if this packet is going to success or not. Okay, then we'll activate the ARC at the initial stage. So this is a kind of very powerful solution if we apply for let's say IoT device communication, where we have very minimal time to find whether the packet is success or not. Okay, so that is another direction we are doing, and another is that this LDPC decoding. So LDPC decoding the iterative methods. Can we develop a AI/ML model? The decoding method, whatever the time taking. So can we reduce this time? Yes.
So for checking, are you still using the dimensional entry or for that also you use the machine?
Sorry.
So for checking the success of the same packet, you are using the conventional.
No, AI/ML. We are reducing the CRC checking concept. We are using this this one. Okay. Hello. I'm audible. Then also even LDPC decoding. LDPC decoding also we are trying to do by AI/ML model, so that the data rate, that the latency can be improved. Okay, so that also another part we are working. Okay, so this is a overall structure. Even channel estimation I missed, STO CFO estimation, those work already done. Okay, you can find some published work. Okay, from my group or many other people are working in this direction. So channel estimation, many papers will find, and STO CFO also will find, and also some parameters. For example, symbol rate estimation, IF estimation. So those are the estimation also we can do by using AI/ML based model. So this is a overall 6G frame structure you can see. Okay, now let us move to any. So I have taken here 3-4 words. Okay, but any of the topics we could discuss. Okay. So the main objective here now again, you can see that those are the blocks. Okay, and at this stage we are trying to replace any of the block by AI/ML model. Okay, but in the what we are trying to do that, just see if we implement a AI/ML block for this, AI/ML block for this, AI/ML block for this, so the complexity also will be increased, right? So now people also are trying to, can we combine those blocks to a autoencoder and combine this receiver block to autodecoder, so that we can do. A lot of work is going on, but a lot of pros and cons are there. But I think one day it may be possible, not impossible. Okay, so this is the main goal, is to you can combine all this block. Okay, so now BMC, I have not given the blind modulation classification, that what I talk this AI/ML based modulation. So it has some pre-history that this AI/ML based modulation, before there was some method is called the blind modulation classification, and many works are there. Just I'll put some light and then I'll move that. I already mentioned that why this AI/ML BMC. Okay, but now we are calling it automated modulation classification. Before, when we used to use some statistical based method, we used to call blind modulation classification, because that time we never used to have any pre-information. But automated modulation classification, there's some distinct. That automated means it is not blind. We are using pre-existing data set to train the model. So it is not blind. But once you train the model, then your model become automated. They don't need any intervention. Okay, so that is only slight difference. Now we think that, as I mentioned, this is a base station, and they have inner circle, they have medium, and then outer circle. And you can see that the path loss between from this one to this one is a very minimal. So whatever signal will be transmitted from here, almost entire signal will be received by here. But in this case, there will be some more path loss, but outer circle there will be more path loss. So now we can see that this, since it has a less path loss, so obviously the user will try to use maximum capacity, right? So maximum capacity means need to transmit some, let's say, higher order modulation scheme, nothing but a 64 QAM. Now for middle circle, they'll use middle 16 QAM and QPSK. You can see that they are the uplink communication. So you just selecting their modulation scheme as per their understanding, their payload, but base station does not know. So then they have to understand that which modulation scheme has been sent by the UAE. So for that they need base station has to understand that what modulation scheme it is. So in this case, this is a UAE and this is a base station. So UAE getting some channel feedback by CSI feedback. Based on the payload, they decide the modulation scheme. Then receiver, base station receive the signal and do the modulation classification. And whatever modulation they find, they do the signal recovery. So the objective is same. This is we developed for blind modulation classification. Objective same. Now we are moving to this automated modulation classification. So there are many works, like all are the feature-based method. Means you extract the features that what could be the signal or that features like some higher order modulation, higher order movement or higher order statistical things, that what could be the histogram or what could be the peak, what could be the frequency. So based on that, you do some kind of feature extraction, and based on those features, later you try to classify whether it is BPSK or QPSK or whatever. Okay. So there are many works. So I'm just skipping. This is this one. And challenges. Yeah. So what are the challenges? This feature-based is a kind of statistical nature, right? So if you are having two different modulation schemes, for example, 1024 and 2048. So if we try to extract the features, and most of the time the features of those two modulation will be, these two modulation will be almost same. So classifying, if it is a higher order modulation scheme, is very, very difficult. Okay. So for 4, 5, 6 is fine. Okay. But if you want to move very large level of higher level modulation scheme, we find almost same features. Okay. That is the one reason that very difficult. Okay. And there is then if there is a channel also, severe channel also, at that time finding those things also very difficult. So that's the reason there are a lot of challenges. So we are moving to this automated modulation classification. So you have to try to understand that the another advantage is there. So once you have to collect the signal that this is a y equal to hx plus n, and these are the same block, just you change either single carrier OFDM MIMO or MIMO OFDM. So once you receive the signal and you train the model, and then you find the modulation classification same. So you see, if we can understand modulation classification for single carrier system or OFDM system, then doing classification by AI/ML model is not very difficult. You can do for other as well. Okay, so that's why we are not going to for all kind of modulation scheme. Here just we are, yeah. So you can use some kind of model. So we have used, we call deep learning based modulation classification or automated modulation classification. So in this case, just a semantic diagram we have given, that how different kind of model can be used to classify the modulations. Okay. So we have given some example for AMC. for OFDM system, and we are having also MIMO OFDM, and we are also having the MIMO systems. I'm just touching this OFDM system, how we have done. Okay, so this you can see it is signal model, receive signal model. So number of symbol in this case L, and then we can see that GL means it has some kind of modulation scheme, and M represent the modulation scheme. Okay, we have used some specific modulation scheme here, and these are the, you can say, number of samples. So number of samples which has some specific modulation scheme, and L is the number of symbol. So you need more number of symbols, and then you concatenate for each symbol. This is nothing but a concatenation mechanism. And then in this case, NS is a number of you can take even one symbol, or you can take based on that NS will be defined. Okay, so this is a total number of samples, one vector you can say. And once we receive this signal, we easily can segregate the I component and Q component, and then we take the amplitude square. Okay, so and then also once we know the I and Q component, we can create also phase signals. Okay, so whenever we receive the signals, one can pass simple IQ component, and one can do some pre-processing of the signal before passing to the model. Okay, and it depends on that which one is giving better performance, and sometimes trial and error method, and sometimes some intuition. Okay, this is for example, in this case, what is the intuition? Because we are using some kind of QAM, 16 QAM and 1024 QAM. So you can see that if you try to see the modulation scheme, they are changing only amplitude and phase. Okay, for QPSK there are 4 phase and amplitude is same, right? For other kind of different kind of amplitude. So that we want to extract the attention, that we want to give some weightage to the amplitude and the phase. That is the reason we are not passing the XMN signal directly to the model, but one can do accuracy maybe 5% less or better. Okay, so that intuition plus the knowledge and experience, trial and error method, that can help your model, that accuracy of the model. Okay, so that you can see that amplitude we are taking and phase we are taking. Then we are concatenating this I component, Q component. This is we are making one signal, and again we are concatenating the amplitude and the phase, and we are making another signal. Now we are using, this is a input and this is another input. So we are creating 2 parallel AIML model. So this is a one model, this is another model, and here we are passing IQ, that concatenation of I and Q component, and this one, this is already published paper, so you can have a look also. And this is also another so that concatenate of amplitude and phase, and we are passing both. And then after some this CNN layer, some kind of process we are doing, and you can see that number of filters 16, 64, those are kind of many iteration. We found that this may be the good, that may be the good. So you have to do the trial and error method and some kind of experience. Based on that, this parameter can be changed. Okay. Now after that, we are getting the fully connected layer. Then this layer, and this is a one model. This is another model. We are concatenating. Then again we are fully connected. Then we are passing to this some kind of deep neural net LSTM model. Okay. So LSTM model is there. Okay. Now fully connected. Then softmax, and from there we are able to classify what kind of modulation scheme is there. Okay, so you can see that LSTM. Okay, I'm not going to this AIML part, but LSTM is a very powerful technique for the communication related signal when classification comes to the nature, because our communication signal all are mostly for the sequential based vector. Okay, so like when we send 101 and 110, they are different meaning, right? So almost all communication signal, they are sequential data. So always try to we have noticed that RNN and LSTM works much better than DNN. It's because of sequential and LSTM and RNN mainly used for the sequential data, time series data, if you see. And here, what we have done, that attention layer. So for what attention that, as I said, that we have to understand, let's say we are trying to classify QPSK and 16 QAM. So you can see that QPSK and 16 QAM, so we need to put a lot of attention to amplitude and phase. So phase of QPSK is different, and phase of phase and amplitude for the 16 QAM is different. There are two types of variation of amplitude and phase also, meaning, okay. So those, then we need to, then next time what we are doing here, so you can see that, do you know the smoothing function? So smoothing function, that we are doing the averaging based on the previous, okay. So here also we are creating a new input xt based on this previous, but we are giving different weight, so that this x1 is giving different weight and x2 is giving different weight. And you can see that this attention layer is nothing but another sub AIML model. So what we have to find out? We have to find out that xt will be specifically giving some weightage to some specific number, and that weightage will be decided by training module itself. Okay. So, and then we pass to some kind of activation function, then we create xt. Okay. And this is some kind of how we create this the attention layer. This is attention layer. It's a kind of nothing but a sub AIML model. Okay. But you can see that here we have used only one attention layer, and it works. It's a OFDM signal. But later we'll try to see that if we apply similar kind of method for MIMO OFDM signal, this modulation classification may not work. Okay, so there actually you need to play the role that, okay, that why it is working for OFDM and why it is not working for the MIMO OFDM. Okay, so that I'll just slightly touch and then I'll move to the next. I'm skipping this one for this all this data model, and there are some results we have done. You can see that we are able to achieve kind of above the 90% accuracy, and those are the some existing 60% accuracy. You can see that. Now the question is that with 90% accuracy, can we able to implement such kind of modulation classification for the practical communication? No. Then how will you compensate another 10%? Because it has to be 100% accuracy. Otherwise, if your modulation scheme is missed, then your entire packet got missed, right? How we can do it? How we achieve? Okay, finally, how we achieve the that accuracy 100% when we do the communication, practical real communication? We transmit the signal, right? But there are a lot of errors, channel error. Even after the channel decoding, still there is error. So you can see that we have to create some kind of other layer. Okay, for example, when you do the communication, we get, let's say, 10 to the minus 5 or 10 to the minus 4. This means there are some error. And we are sending million of packets, right? And one packet missed means how do we correct that? We apply again error correction. But still error correction is not 100%. It will be giving the 6 to 5 dB advance. But then we go to redundancy. That is taking care that still if there is error, then that has to take care. So now if we need to compensate the 10% error, no. So we have to also wait till this CRC checking, the packet success or HARP. And then we have to develop a new kind of HARP. Because HARP, usually we define that most of the time packet gets success, and when there is no success, some probability kind of things we apply so that we give a lot of weightage to the success. But in this case, we need to redesign our HARP as well. We could able to achieve 100%, but there are some lot of work need to done in the MAC layer as well. That is my things. Okay. One thing, and second thing is that still this is a preliminary study. We can make, let's say now we are using only LSTM. Can we develop some large language model? Can we improve further 5 dB? Can we apply some kind of recursive, like some kind of recursive or reinforcement learning, something that we can be able to intervene? Now we are not only supervised, but so such kind of model also we can do. Means whatever the accuracy we are getting, this could further be improved. Okay, and if it is not able to reach 100%, we have looked some kind of algorithm in the upper layer. That is the things. And so this is another simulation setup. This is a okay. So then now our thing is that, so that time I exactly forgot that what kind of STO CFO introduction was there, but we reduced this STO CFO. Yes, that also I forgot to mention that STO is only 2 samples. CFO is 0.2 samples. So these studies actually initially along with this blind modulation classification. So objective of blind modulation classification, do the modulation classification as early as possible. As early as possible. The reason was that blind modulation classification mainly used for some kind of army military applications. Okay, so there you may not have other kind of information. But once we apply this for the 3G, 5G, 3GPP or 6G, so when do we need this modulation classification? We need this modulation classification at the last stage. Last stage means that before demodulation, right? So that at the time our PSSB, SSB, everything's done. Even channel estimation also done. So once we do this, and this is not without the channel estimation. This is before the channel estimation. So if we can reduce this 2 to 0, this is 0, this is 0, because we have single carrier system, we already have done Costas loop, we have already done the other kind of error correction, so those are 0. So that even here we could able to touch even 98, 99%. Okay, so you can think it is not impractical doing a modulation classification, and just if you do where you want to put your AI/ML model. Okay, that's the matter. Okay, so that so may thinks that okay, it's very easy for single carrier system. It may be very easy for OFDM system. Is it okay to develop some kind of advanced like RIS assisted MIMO OFDM systems or 5G systems? Now you see that we have given some kind of frame structure. Obviously, if we apply the previous single attention layer, it may not work. Okay, but that's the reason we also bring some other kind of attention layer. You can see here, I'm sorry that it's not maybe visible. So you can see, but this paper also available in the published form. So you can see that here we use the 3 kind of attention layer. That facial attention layer, that is because of the MIMO. We are bringing this attention layer, channel attention layer, because RIS has a double fading effect. Okay, so we need to put little bit more attention to this double fading effect. Okay, and then also dilated attention layer, that is another attention layer. So you can find in the details in the paper. So these 3 mechanism we are applying, and then we have done the modulation classification. So other than that, is almost same model here. Same model here. Just we have changed this attention layer to the 3-level model attention layer, and here some parchments has given, and you can see that we have done for the 2x2 MIMO OFDM system, and also we have done that M is a number of elements, and then we can see that this is a proposed method, so almost 97 or 98% accuracy, and also we have done for the different kind of channel model. Okay, so these are the different kind of channel model we have taken, and we also have compared some existing work like ResLate, CNN model. Okay, this is a bi-stream LSTM model. So these are the different models, and we have applied, and we have seen that, it's not that whether our performance is better or not. So that is a publication issue, but usually we could able to reach 95, 97% accuracy. Okay. And again, for those kind of, again, that CFO presence was there, STO presence was there, but if we remove those, and if we also remove the channel estimation error, then we could able to reach again 98, 99%. And 1%, 2% is present everywhere, right? Those we can find other way to resolve it. Okay. And you can see this is a confirmation matrix accuracy, and we have done the beauty of this one, we have reached till 1024, means what 5G support till 1024 as per the technical specification, right? So we could be able to classify all the modulation level. Okay. So this is just, I touched only open problem. This two-sided model, what I discussed, we have not also implemented. One can look into this, that whether we can able to develop two-sided model. So transmitter will predict what modulation scheme is suitable for better quality of service, and receiver do the recognition. And the last one is that based on, I'm also working in these two part also I'm working. So AIML based nonlinear modulation and demodulation. So that already 5G release 20 also looking the same problem. The second one, first one is much more advanced maybe, but this one already there are some study work is going on. Okay, so one can look into this, that how AIML based nonlinear modulation and nonlinear demodulation can be performed. Okay, so channel estimation. So that channel estimation, but the advanced topic is that channel prediction. So channel estimation means what is that? You are estimating the current channel, but when we need to do the channel compression and feedback, okay, so there is some kind of time consume is there, a lot of things. Can we predict the channel for the next time slot? Okay, so that work also going on, but it's not very easy task, but it's possible maybe. But then we use some kind of DNN model, and just a basic things of how we prepare the training, how we prepare the testing, then how many hidden layer is there. So many things are there. So I'm not going details that how to prepare the data. So hidden layer, output layer, how to create loss function, how to do the training out of 70% or 80%, then how we do the feeding, all these things. Okay. So then I just moved to some channel. Okay, I need another 5 minutes, then I can able to conclude. And then yeah, so this is a frame 1, frame 2, frame 3. So actually how do we decide the frame 2? So frame 2 is a nothing but a duration within the coherence time, and within this coherence time, here we divided two symbols. This is a one symbol pilot, this is data symbol, but it is not always this pattern we need to follow. We have to have some frame, 1 or 2 frame for pilot to estimate the channel, and that estimated channel we can use rest of the frame until the coherence time, because once we cross this coherence time, then the channel will be changed. So we cannot use whatever estimated channel. That understood, right? So here we assume that this is a coherence time, within coherence time, and we are estimating from here, and that estimated channel, in this case data is known, we are estimating channel, and here channel is known, we are estimating the data. And this estimation we can use LS, we can use MMSE, we can use LMMSE. Okay, so now can we apply so AIML model? So when we do LS, we don't need any pre-requisition, just we get the signal from their pilot based. Okay, but when we use MMSE, we need also LS. We do the LS, and knowing okay this is LS is known, then we do the MMSE or LMMSE just to reduce the complexity. So now, then we can estimate the channel. Then what we do? We compensate that channel by equalization method. Then we get the detection. But what is the main objective? Main objective is not to estimate the channel. Main objective to estimate the data. So channel estimation, unless otherwise you do the feedback, then channel estimation part not come to the pictures, right? So now can we develop some kind of AI ML model where we will not estimate the channel, but instead we will estimate the data itself, okay? So that some mechanism we have developed here. It's not our work, it's a some existing work. Our work little bit much, so we need to first understand this one, then we can move. So this is the mechanism. So what is the mechanism is that data generation, and then I have the formation of WaveDM, then receive signal. So we remove this CP and this is the data. Okay. So now what we'll do, we'll pass this data and we'll pass this data to the model. You see pilot and data, but we'll not estimate all the bits. We'll estimate only part of the bits. Why not all the estimate the bits? Because if we estimate all the bits, so that accuracy degrade. But if we estimate only few bits, estimate improve. Then how do we estimate the other bits? So then we can create a parallel mechanism. So what parallel mechanism? From this frame, we estimate these bits. Then we create a parallel of AI ML model. Why we are creating parallel? Because the complexity, everything will be the same because we are making parallel mechanism. So from this data, we will be estimating only 0 to 15 bits. This model will give 15 to 16 to 31 bits and so on. Then we can able to get all these bits. Okay. So this is a better, instead of channel estimation, we could say this is a symbol detection. Okay, symbol detection. Then this is a model, and then there are some performance. This is some example is given deep learning methods. So these are the results, and you can see that deep learning also equivalent to giving the LMMSE performance. And there are many work, that this is a very low complex channel estimation methods. Okay, this is, I'm just skipping. I'm just touching that what are the other things is possible. So that IF carrier estimation. So intermediate frequency estimation. This is another things we do for satellite communication. We do for military communication, and even we do this IF estimation to remove the Doppler effect. Okay. So this is one work we have done, and we have checked that compared to the statistical based method, and this is a AI ML based method, and performance is very good. So this work we have done. We have also done the symbol-led estimation. You can see that symbol-led estimation. This is a statistical based estimation, and this is and we have this work very old. We have done those 2018 or 2019, and in terms of accuracy, and we have used simple DNN model or sometimes CNN and DNN, and this way. This is very old work. So, but just I'm saying that, and now the question is that where we can use this SIF and symbol-led estimation in 5G. There is a called numerology. So we change the numerology, like we change the symbol duration, sub-carrier spacing, okay, and those things we put some table, and receiver also same table, and we extend the index. So you see, for the modulation scheme, we use some kind of index. Here we are using another index. Now, when we create a dynamic nature, either data rate, either symbol sub-carrier spacing. So every time we store a lookup table at the transmitter, lookup table at the receiver, and we send the index. Now, if we combine all these things, see how much that data or index need to be transferred. That those are the redundancies, and that is the reason in 5G, 6G, whatever data we send, the overhead is 20 to 40%. Depends on the things, all the control signals. So they are the kind of control signals in the overhead. So can we reduce 5%, 3%, 1%? And those are huge if you can reduce. Okay, that is the main goal for the AI ML adaptive communication systems. Yeah, I will conclude this my talk here. These are the some advanced research means you can do for just I mentioned, this is a one open problem, sub-carrier spacing, cyclic prefix, other parameter estimation. I have already discussed, symbol already discussed. Timing frequency synchronization, like PSSB, SSB, primary synchronization block, secondary synchronization block. Those block, if we develop a AIML, again, the performance accuracy synchronization may be much better. Spectrum sensing is another topic, and for 5G, for private 5G or private 6G. So this spectrum sensing will play very major role. Okay. Then adaptive interleavers, Camler, already I mentioned. Channel encoder, decoder, LDPC, that can we use the LDPC, and PAPR reduction, already I discussed. CSI compression and feedback, already a lot of work already has done. Okay. Oh yeah, that's all. Yeah. Thank you very much.
Just one last question.
Yes.
So, sir, like your main objective of the talk was to reduce the gap between simulation and the practical application. And you said that
That is only one fundamental. That is one, only one.
but you said that you're using activation with the networks, and generally you always talked about data. So it's supervised machine learning. Now the thing is that when we want to reduce that gap, so are there like any particular data sets available which we can use for training our models, or do you generate your own data?
So, okay, good question. So always I say that what is the difference between practical data and then synthesis data? What is the difference? First you to understand. Practical data and synthesis data. You see, all communication signal is manual. Do you agree? Yes. Then whatever destination will generate and whatever I generate my simulation, there is no difference. Only when those data passes through the channel model, that makes the practical and synthesis, right? Now, do you think that even whatever the practically we implement channel model, they are all practical? No, there is some channel model for types. Of course, some channel model empirical, some other people they develop channel modeling by mathematically, and those channel modeling almost exactly same with the practical channel modeling. So if we use a proper channel modeling, then you can use your own data. You don't have to rely on any data set at all. Okay. And for synthesis, now then the transfer alignment also is there. You develop a model by your own data without practical channel modeling itself. Okay. Then later on, when you will be deploying your model somewhere else, okay. So that time you capture your practical data and we then tune the model. Just you need to tune the model by using the transfer learning. That's all. You may need only 1 second or 2 seconds to retune your model. Yeah, that's all.
Okay, thank you. He need to rush to airport. So if you have any question, just email to him because his flight is preponed by 1 hour.
Yeah, thank you.
So
Thank you.
his flight is at 12:30. Now it's almost 10:05. Yeah, thank you, Professor Majhi. So we
Thank
have
you very
some audio.